I'll start off with an overview of our unmanned aerial system. Our vehicle, the V-14, is a quadcopter highly optimized to balance payload capacity and great autonomy. Its most efficient configuration weighs in at 22 pounds, including all required payloads for the tasks, and can fly 40 minutes. The first payload is the vision system, consisting of a motorized 3-axis gimbal and a smartphone. It has a powerful 40-megapixel camera with optical zoom and acts as the onboard computer. The live video feed and captured images are transmitted in real time to the ground station with our tracking antenna. The images are analyzed using our software to find the coordinates of the objects and to communicate the result to the interrupt server. The second payload is a winch that will deliver the unmanned ground vehicle from an altitude of 100 feet. The UGV is itself equipped with all sensors necessary for autonomous driving, including the GPS augmented with real-time kinematics. Our ground station runs custom software to generate a flight plan adapted for the mission and to easily analyze images for object detection. As for the planned tasks, we will be attempting all of them except for the autonomous object detection. We are highly confident that we will successfully complete the tasks given our track record and our tests. Brahim and Kevin will present our development testing strategy.
Our testing strategy is to first test every compound individually before attempting to use it in flight. Once we are confident that each compound performs as expected under controlled conditions, we start testing them in flight and in conjunction with other subsystems. We use simulation to validate some subsystems' performance when testing in true conditions was not possible, such as our dynamic obstacle avoidance system. To test the autonomous flight performance of the aircraft, we started by flying short missions with manual takeoff and landing. This test allowed us to tune the V-14 and adapt it to autonomous flight by changing the speed, tuning radius and waypoint mode. We then go to fully autonomous missions with takeoff and landing to tune parameters like vertical speed and takeoff altitude. These are especially important to test for different wind conditions. Over this test, we accumulated 11 partial autonomous missions and 14 fully autonomous missions. The pilot spent on average under 2 minutes taking control in manual mode for takeoff, landing, and mission interruptions. The airframe's waypoint accuracy is too high thanks to our autopilot and RTK augmented GPS. After the mission is uploaded to the drone, the autopilot has no problem executing the mission with high reliability. We tested more than 250 waypoints and the recorded position of the aircraft was compared against the waypoints to calculate the average error, which was less than the acceptance radius of 5 feet configured in the autopilot. All the waypoints were hit for the 8 test flights. Obstacle avoidance is done by calculating a flight plan before takeoff that will optimize the mission timeline going through all points of interest while avoiding static obstacles. This was tested by creating mock-up waypoints tasks with obstacles of various sizes and generating a flight plan. We observed the path planner to ensure that it had a good performance both in path length and in execution time. The aircraft performed over 500 obstacle avoidance during testing.
For the imaging system, images of targets of known size were taken at various altitudes to confirm the theoretical object resolution that was calculated during development. For example, at 125 feet of altitude, we have a 2.5 pixel per inch resolution, which is enough to distinguish alphanumeric characters and colors. To ensure the best image quality, images are taken at a maximum resolution greater than 4K to allow for digital zoom. The gimbal keeps the camera pointing down to keep the maximum surface in the field of view and limit distortions when objects are close to the edge. To test the object detection and classification, mock objects were placed in a field for mission test. The imaging operator was able to detect over 90% of the objects and correctly identify the alphanumeric characters in all cases. The color and orientations were identified correctly most of the time. These tests were also used to gather data for our future object detection and classification algorithm, mostly in the form of hundreds of test images containing objects on different backgrounds. The object localization was tested by placing targets at known GPS coordinates and using the imaging system to find the location. Out of 28 attempts, 24 estimated localizations were within 20 feet of the true coordinates. We also compared manual localization analysis to our software and found that there was no significant difference in error between the two approaches. The mapping software was first tested using image data from previous tests and competitions to ensure the quality of the maps using suboptimal conditions such as angled images and missing metadata. Once more images were gathered using the gimbal during our other test, we created maps using images in the same conditions as the mission demonstration. In all tests, the coverage was complete. We then proceeded to compare the resulting maps to map providers like Google Maps to evaluate the quality. Finally, we tested the precision of the winch by programming a mission to a known coordinate, lowering a weight to the ground, and measuring the distance from the known location. Over 5 tests, we averaged an accuracy of 5.4 feet. The ground vehicle was tested in controlled conditions and on different surfaces using an autonomous mission to tune its autopilot. I'll let Alexander conclude with the mission testing.
We prepared for the full mission by practicing each task individually and then by attempting multiple of them at once in the same flight window. One of our test missions started with a 2 miles flight in a field. We followed 16 waypoints while avoiding 10 virtual obstacles. We found and identified 11 out of 12 objects and then dropped the rover within 5 feet of a target. We kept communication with the interrupt server, sent our telemetry, and sent all object information within 5 minutes of the end of the flight. This type of test let us practice for all the tasks, except for the UGV driving to location. This was done in a controlled environment. We also timed ourselves to keep track of our progress and ensure that we were within the time limits. We had the opportunity to practice complete mission by participating in a competition hosted by the Aerial Evolution Association of Canada. This experience allowed us to find some flaws in our communication system. For this reason, we swapped the main RC antennas of the aircraft from 2.4 GHz to a previously tested 433 MHz solution for added range and reliability. We also used a different vision system that will now act as our backup for future mission. In the same way, we found that when integrating our camera with the gimbal, a cable connecting the camera to the onboard antennas would tend to get stuck and was too stiff for smooth rotation. The problem was fixed for future tests by simply swapping the cable for another type. Considering the full mission test, this is our expected score. We have a high confidence in multiple systems that were used in past competition and were extensively tested, such as the obstacle avoidance system and the autonomous flight controller.
From the whole team, thank you for your attention and see you in June.